Hello, this is mathjazz from Almost Cool, and this is another calculus live stream. I have some problems for us to work on, and I will, of course, be taking questions in the chat when they arise. So, um, thanks for watching, and let's move to our first problem. Problem 1. I felt like doing a bunch of trigonometry questions and limits today, so that's what I have set up for us. The first question is, simplify the following. Sine of tangent inverse of x. And so we're going to need to draw a triangle. Let me get our triangle ready. Here we go. So we draw a triangle. We need to have very thick lines because it's kind of hard to see on YouTube when we don't have nice big lines. Here we go. Here is our right triangle. So now we go back to the statement of the problem. It says we know that tangent of our angle is x. That's what it means by arctangent of x. It means that for our angle here, which, well, let's see, we'd really want to have a theta. Maybe I can pull a theta out of our Mathematica here. There we go. It's kind of hard to put Greek letters into Microsoft Paint. Here, we have our theta. Let's make it a big one so we can see it nicely. That looks nice. Yeah, that looks really nice. So we have a theta there, and we know that tangent of theta equals x. So that means that the opposite side divided by the adjacent side is equal to x. A little bit of a mismatched font here, but that's fine. And now we're looking for sine of our angle theta. Well, sine is the opposite over the hypotenuse. So what we want is to have this x divided by whatever the length of the hypotenuse is. So, well, we're going to use the Pythagorean theorem. The Pythagorean theorem says the hypotenuse is equal to the square root of the square, or sorry, the sum of the squares of our other two sides. Now, the square of 1 is just 1, and the square of x is x squared. So this shouldn't be too hard for us to be able to compute. Fantastic. So now we know that the opposite, this x here, divided by the hypotenuse, which is the square root of x plus 1, is equal to sine of theta, which is equal to sine of arctangent of x. So we will write that up here. Sine of arctangent cotangent of x is equal to 1 divided by the, x divided by the square root of x squared plus 1. And I guess our Mathematica wants to tell us that that is a true statement. There we go. So that's our first problem down. Now we get to see what our next problem is. So, problem 2. Simplify the following. Secant of cosine inverse of x. Maybe some of you have realized it yet, or already, but this is a trick question. Since secant, well, it's almost a trick question. Secant is equal to 1 over cosine. So that means the secant of cosine inverse of x is equal to 1 over the cosine, 1 over the cosine of the arc cosine of x. So secant of arc cosine, let me type this in, of x is equal to 1 over the secant of the arc cosine of x, 1 over the cosine, of arc cosine of x. But arc cosine and cosine are inverse functions. So that means that they just cancel. We get 1 over x, like so. Let me put a couple of parentheses to help Mathematica out. There we go. So secant of cosine inverse of x is equal to 1 over cosine of cosine inverse of x, which is equal to 1 over x, because cosine and inverse cosine are inverse functions, and they cancel. Let's do another. Here's another trigonometry question. Simplify the following. Cotangent of sine inverse of x. So we're going to need to grab our triangle again. Let's pull that up. So sine of theta equals x, and sine is equal to the opposite over the hypotenuse. So that means that we'll just undo this here. We know that x over 1 is equal to sine, so x is the opposite side, and 1 is the hypotenuse, or 2x is the opposite side, and 2 is the hypotenuse, whatever you want to pick, so that when you divide the opposite by the hypotenuse, you get x. I chose x and 1. Now, we wanted to know what the cotangent was. And the cotangent is going to be the adjacent over the hypotenuse. So let's give a name to our adjacent side. We'll call it y. And then what we know from the Pythagorean theorem is that x squared plus y squared has got to equal the hypotenuse squared. The hypotenuse is 1, so this x squared plus y squared equals 1. There we go. Well, we want to know what y is, so we have to subtract x squared to the other side. So we get y squared is equal to 1 minus x squared. And we take the square root of both sides. So that gives us that y is equal to the square root of 1 minus x squared. Like so. Now, we know the opposite side, which is x, and we know the adjacent side, which is the square root of 1 minus x squared, and dividing the adjacent side by the opposite side gives us cotangent. So let's write that in. So, cotangent of sine inverse of x is equal to the square root of 1 minus x squared divided by x, like so. So let's move on to the next question. I think this is problem 4. Yes. Okay, so this one is a little bit tougher. So instead of having sine of tangent inverse of x, we have sine of 2 tangent inverse of x. And we're going to have to deal with that 2 there. I find that the easiest way to do this is to use the double angle formula. So one thing that we do know is that sine of 2 tangent inverse of x is, well, our double angle formula says that this should be equal to 2 sine of arctangent of x times cosine of arctangent of x. And now we just need to figure out what sine of tangent inverse of x is and what cosine of tangent inverse of x is. And for that, let's go back to our triangle. So if tangent inverse of x, sorry, if tangent of theta is x, see, tangent theta is x, that means that our opposite side is x, and our adjacent side is 1. So, here we go. Here's x on the opposite side and 1 on the adjacent side. And this will give us the, via the Pythagorean theorem, the square root of x squared plus 1 as the length of the hypotenuse. So now we need to know what the sine and the cosine of this are. Well, the sine is going to be the opposite over the hypotenuse. That is this one over this one. And the cosine is going to be the adjacent over the hypotenuse. So let us go use those in this equation. So we're going to get 2 times the opposite, which is x, over the square root of x squared plus 1. And then we're going to multiply that by 1 over the square root of x squared plus 1. And that gives us 2x over, well, the square root of x plus 1 times itself is just going to be x squared plus 1 in the denominator. So let's simplify that. There we go. So simplifying this trig expression gives us 2x over x squared plus 1. Okay, so let's switch gears and start talking about limits. Here is problem 5. We want to evaluate this limit. So the first thing that we want to do is we're going to divide the top and the bottom of this fraction by x squared by x squared, since x squared is the highest power that appears in either the numerator or the denominator. So let's do that. We get 1 plus 1 over x squared divided by 3 minus 2 over x squared. Since we divided on the top and the bottom by the same number, that is x squared, it doesn't change the value of the limit. And now, if we let x go to infinity, we see that the the 1 over x squared term in the numerator will die, and the 2 over x squared term in the denominator will also die. So this thing here will equal 1 divided by 3. Not too bad. Let's see our next problem. Problem 6. We want to evaluate the following. The limit as x goes to 1 of x squared minus 1 over x squared minus 2x plus 1. So the first thing that we need to do here is we're going to have to factor the numerator and the denominator. So the numerator factors as x plus 1 times x minus 1. And I bet I'm going to need parentheses to keep the fraction together. The denominator factors as, well, x minus 1 squared. like so. If we cancel the terms in the numerator and the denominator, well, I guess we didn't need to factor, but factoring is nice. This is nice practice of factoring anyway. We could have just gone directly to dividing by x squared on the top and the bottom, and that would have been fine. Oh wait, no, we're not going to infinity. I got confused. We're going to 1. We do need to factor because we're going to x is going to 1. Let me fix this limit. There we go. X is going to 1. So we do need to factor, and now we will cancel. So we'll get the limit of the fraction x plus 1 over x minus 1 as x goes to 1. There we go. And now, looking at this, we've canceled all of the like terms, and we notice that when we plug in 1, we're still going to end up with 0 in the denominator, and we'll get 2 in the numerator. So this means that this limit doesn't exist, and further, if we're coming from above 1, we get a positive number over a positive number, which is positive. If we come from below 1, we get something less than 1 plus 1 is positive when we're close enough to 1, and a negative number. So the limits from each side go to different infinities. Let's see a graph of that to demonstrate. Plot x plus 1 divided by x minus 1, and we'll just look at the important part, which is from like 0 to 2. And we'll make the lines thick enough for you guys to see. Maybe a little bit thicker than we needed, but that's fine. There we go. That's probably the right size. Notice how we go up to infinity on the right, and we go down to negative infinity on the left. So this limit doesn't exist. Okay, so let's go to our next problem. I think that's problem 7. Evaluate the following limit. The limit is x goes to 0 of sine of 2x over x. So, what we know already is the limit of sine of x over x. And we know that that is 1. This is a limit that as x goes to 0. We know that this limit is 1 from memorization. Maybe I'll make a video proving it in the future, or I guess I might have already made a video proving it. I'll have to check. But this is one of 3 limits that students are typically asked to memorize in a Calculus 1 class. So knowing this and looking at this, we see that there's a big similarity. the problem is that this number does not match that one. But we can manipulate this limit so that we can use this limit that we know exists in its calculation. So let us do exactly that. Here we go. So the limit of sine of 2x over x as x goes to 0 is equal to, well, if I multiply on the top and the bottom of the fraction by 2, then I won't change the value of the limit, like so. I'm multiplying on the top by 2 and on the bottom by 2. So I don't change the value of the limit. And of course, constants can be pulled out of limits. So we get this. So now, looking at this, this goes to 0 at the same speed that this does up here. And that allows us to use this limit via substitution. So we know that this limit is equal to 1. So we'll write that in now. There we go. So since this limit equals 1, 2 times 1 is equal to 2 times 1, which is equal to 2. And we have solved this limit. We have found its value. And now on to our last problem, unless there are problems in the email, which we will check. Evaluate the following limit. Well, the first thing we want to do is we want to factor, because x is going to a finite number and we have a rational function. So we'll have to factor and cancel all of the like factors from the numerator and the denominator. So we start off with the limit of x squared minus 1 over x plus 1, x squared plus 1. And that should equal the limit, well, when we factor it, we're going to get x minus 1 times x plus 1 in the numerator. And in the denominator, we can't factor. Now, since we can't factor in the denominator, we, well, at this point, we'll just plug in 1 to see what we get. If we get that we're dividing by 0, then the limit won't exist because we've canceled all the like factors because there aren't any like factors. We just proved it by factoring the top and finding that the bottom is unfactorable. And if we wanted to prove that the bottom is unfactorable, we could use the discriminant in the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. So the discriminant is the b minus 4ac part. Sorry, b squared minus 4ac part. So b in this polynomial is 0. So 0 squared is 0. And then minus 4 times 1 times 1 is 0 minus 4. That's negative. Negative means that there are no roots of this parabola, which means that we can't factor. So, since we know that we cannot factor the denominator, we know that we've completely canceled all of the like terms in the numerator and denominator because we've factored everything as far as we can go and there's nothing that could cancel. So now when we plug in 1, whatever we get is going to be the value of that limit. So we do that. When we plug 1 into the top, we get 1 squared minus 1 is 0. And when we plug 1 into the bottom, we get 1 squared plus 1 is 2. So we end up with 0 as the value of the limit. Like so. Okay, so let us check our email and see if we had any last-minute requests. And I do not see any more questions. Okay, so since there are no more questions, say thanks for watching. I hope that you are enjoying learning calculus, and I am very grateful for all of my viewers out there. Good news. So yesterday, when I checked my view count, I had 1,004 views across all of my videos. So we have broken 1,000 in the number of views, which is a fantastic goal, and a really it makes me feel good to accomplish that. The next goal that I'd like to see us reach is to get 100 subscribers. So far we're at 34, and that's not bad because we've only been in the channel. Almost Cool as a whole has only existed for about 8 months, but this channel has only had videos since September last year, and so uh, I am greatly appreciative to the 34 of you who have subscribed to the channel. And if you could tell other people to subscribe to the channel, give them my email address, and have them send me questions, and I will answer them. I would love to do that. And again, thank you so much for your support in watching this channel. I hope you have a great day. Thank you, and goodbye.